All right. So, in electrostatics, we often deal with like electric point charges and stuff. So, for example, if you had like, I don't know, proton or neutron, not neutron, that's neutrally charged. But if you had like a proton or electron, and obviously in this case we have a proton, you can also have an electron here. Hey, opposites attract. There's going to be a force between them, a force of attraction, right? And we call this the electric force. And when you start off with learning this stuff, you get introduced to Coulomb's law. So Coulomb's law says, hey, the force of attraction, or just any sort of force, right? Because if you had a proton, positive charges kind of repel. Same with like electron. So the overall force of the electric force is going to equal some number k times the charge of one of those things times the charge of the other, charge over the distance between them, r squared. And k is, it's a constant. It's 9 times 10 to the ninth newtons per, right? This is going to be newtons, so if you think about the units, right, you have Coulomb squared over meter squared, so this would have to be meter squared over Coulomb squared. And this equation, yeah, very similar to like the FG equation, and it's pretty useful in a lot of cases. But sometimes, it's not always like one single point charge. You could have something like, I don't know, maybe you have a rod. All right, you have a rod, and the entire thing is uniformly distributed with a positive charge Q, and the electron has its charge being negative E, the elementary charge, and then what you realize is, okay, we can't just use this equation. Well, we can use this equation, but what we have to realize is, okay, there is a point charge here, and there's a point charge here, and it's made up of a bunch of these point charges, these very tiny amount of charges, and they're each a separate distance away. So the charge right here on this part of the rod is much closer by Pythagorean theorem, right? It would be much closer to the electron compared to the charge here, and you would have to do some calculus, right? If you want to figure out the force of attraction, or better yet, if you want to find the electric field, right? Because the electric field, Fe, or the electric force is equal to the charge times the electric field, and the electric field is equal to K times Q over R squared, right? Q meaning the charge that causes that electric field, right? So this electron has its own, creates an electric field, so does a rod, well, all these different point charges and stuff, and when you plug that back in, you just get Coulomb's law. But, yeah, if you want to find like the electric field at this point or something like that, well, you're going to have to do some calculus. You have to say that, hey, this dq, this little amount of charge, right, a little amount of electric field, and then you have to worry about the x and y direction, right? So dex, like the x direction, when you have symmetry and all that, it can be a complicated mess. And a scientist named Gauss was like, hey, I don't want to do all that. So, not scientist, I think it was a mathematician, I don't know actually. But Gauss's law helps resolve and makes this process a lot easier. So, I'm going to talk about Gauss's law. But before we get into Gauss's law, we got to talk about electric flux. What is electric flux? Let's say we had an electric field. So let's say there is, let's say we had a sheet of paper. So this is the top view of a sheet of paper. So top view. Now if we had like the 3D kind of view, right, we're just looking at the top, you would have a sheet of paper like this, right? And then we have, I'll say regular. Then we have, let's say we have an electric field passing through the sheet of paper. So maybe it's like, maybe the sheet of paper is in between a parallel plate, right? And parallel plates have a uniform electric field, so we'll just say the electric field is uniform, right? So no matter what, point you're at, near this thing, it's going to have a uniform electric field passing through that sheet of paper. And if we were to draw like that, view, like the 3D view, right, you would see the electric field line passing directly through the sheet of paper, right? So if this was a top view, everything is kind of perpendicular. the amount of field lines, so conceptually, if you think of, like, if, you know, conceptually, the electric flux is really just the amount of field lines passing through that sheet of paper. So, how do we get more electric flux? Well, you can do a few things. First of all, you can make, so let's say there's, you know, electric field everywhere, right? Because it's a very big parallel plate. Hey, if you want more electric flux, just make the sheet of paper bigger, right? You're gonna get more, and then you would also see getting the, you know, thing bigger here. Hey, more area means more electric flux, because electric flux is the number of field lines passing through that area. If you made the electric field bigger, right, a stronger electric field, something with more charge, right? If you think about Coulomb's law, hey, that's more electric flux because same area but more electric field. And another way you can actually change the electric flux is like, okay, we have an electric field like this. What if instead of doing it completely perpendicular with everything, let's do it at an angle, right? If we were to make this, horizontal, then there would be more electric field lines, so the angle also changes the amount of flux you're getting, right? Because if you had, this is a sheet of paper and it's parallel with the electric field, and remember this is the top view, then now there's no electric flux. So the electric flux, we use the symbol phi, I don't know, something like that, and I'm almost dropped my marker. The electric flux is equal to E, the electric field, times A, this surface, times cosine theta. So let me kind of unpack this a bit more. We can see that this is some sort of it's kind of linear everything, right? I guess except for theta, but this is kind of just a dot product, right? You're taking the dot product of the electric field, which is a vector, and the area. You might be saying, wait, area is not a vector, right? It's just like area. Like how does area have direction? Well, what people, like, the convention is, if you had a sheet of paper, the direction of that area is going to be perpendicular to that surface. So if you get that 3D view again, right? In this case, it would be it's kind of hard to draw with all the angles, but it would be something like this, where it's sort of perpendicular with the that doesn't look right. Let's do, yeah, there you go. That still doesn't look right. Wait. There you go. Now it's going to be perpendicular with the surface. So that's kind of the direction. So if you're like, the theta is going to be the angle in between. So if you had, if we go back to, this is our electric field, the angle between the perpendicular of the surface, because that's the direction of the area vector, it's 0 degrees, right? It's completely parallel compared to if we had it, the sheet of paper, like sort of, parallel with the line. Well, now the vector is going to be pointing perpendicular to the field, so the angle in between is 90, cosine 90 is 0, there's 0 electric flux. So there you go, that's kind of electric flux. Now, this is kind of like for a surface or sheet of paper. Let me just check how much time I have. I need to do a better job. Okay, 8 minutes, that's not bad. We also got to talk about enclosed surfaces. So for electric flux, that's where things can get kind of useful when you look at enclosed surfaces. So I'll just leave this equation up, but hopefully this equation kind of makes sense, right? More electric field, more electric flux. More area, more, what's the word? Electric flux. Theta, if theta is 0, right? If everything, right? If the surface is, the direction is like parallel with the electric field, most electric flux, and if the angle is 90, then there's no electric flux. And remember, when we say angle is 90, we don't mean like this. We mean the perpendicular of the surface. As I just kind of explained, just wanted to hammer that in. So if we had, let's say, a point charge, an electron, and let's say we encompass a kind of box around this thing. So I don't know how I'll draw this. So this is maybe a side view, right? And if we had the 3D view, it would look something like this, maybe. Okay, and then we have the charge kind of in the middle. So let's say we want to figure out what is the electric flux on the top face, right? So just like how we had a surface, let's just try to figure out what is the electric flux for that top face. Well, we're going to do the same thing. We're going to look at the electric field, and we're going to look at the area, and we're going to try to figure that out. Well, guess what? Let's say this is also in the middle, by the way. Well, now, if you even just try to visualize it, it's not going to be everything. The electric field is not going to be uniform. It's not going to be uniformly piercing through the surface. It's going to be kind of at an angle, right? It's going to be kind of, well, not at an angle, but it's going to be coming in all sorts of directions because it's kind of like a sphere. So what that means is, if we had, let's say this was, and let me kind of erase this. So I just to show you the electric field is kind of everywhere. It's not uniform in one direction. If we were to think about Coulomb's law, I should just use an eraser. I don't know what I'm doing there. If we were to think about Coulomb's law, well, the electric field right here, this is going to be, I don't know, a distance d, right? Half this cube, if this is like a cube, right? Half the length here. And then this is going to be a diagonal. It's going to be a bigger distance. I don't know, root 2d. If the trig is right, it should be root 2. Point is, this is a bigger distance. If we think about kq over r squared is equal to the electric field, well, now there is a bigger r, so less electric field. There's less electric field here, and there's going to be less. And remember, it's also like a cube, right? So we have here, we have an electric field here, here, all these different points. The electric field is going to be different because of this equation. So, I just knocked. You can't really use this equation anymore because it's like, hey, the electric field is not constant. I want it to be constant in order to use it. So I have to be, I'm going to have to do the sad thing where, hey, a small amount of electric, that's not the right symbol, a small amount of electric flux, d phi, is going to equal a small amount of the electric field at that point times, well, not d, but it's going to equal the electric field at that point times dA. Actually, wait. I haven't taken calculus yet fully, so my notation might be wrong. But whatever. dA dot dA cosine theta. We're going to have to, if you integrate both sides, you would get that the total electric flux for that face is going to equal the integral of the electric field dot dA. Or I'll say multiply by dA cosine theta. So, it's an integral, and it's a closed surface, so we actually put the circle here for a closed integral, but that is the true equation for electric flux. So if we have the real equation is going to be phi is going to equal, I think it's phi, or it might be, I think it's phi. Phi is going to equal the closed integral of the electric field, times dA cosine theta. What if our electric field is constant for the whole area? Well, then you pull the E out and then you integrate. Oh, you just get the electric field is going to equal EA cosine theta. So remember, this is for a constant uniform electric field, and the way you know that is in this integral, which is the true most general form. E is constant, you pull it out. If you're integrating dA, you're going to get the full area. So boom, this is the constant version, and this is the general version. We're going to look at this a lot for Gauss's law, which is why I wanted to make a separate video just explaining electric flux. It was really confusing for me, but hopefully that makes sense. Now I'll go on to part 2.